Alright gang, here we go. This is for Physics Unit 9 Part 6.2, talking about complex resistor calculations. Now this, my friends, is where the rubber meets the road. This is where you get to check all of your knowledge you've gained in Unit 9. This is it, alright? So, we're going to do a couple of things. What you need to be able to do by the end of this video, or by the time you're done practicing the stuff in this video, is you need to be able to calculate the equivalent resistance for a complex circuit. And when we say complex circuit, what we're saying is that a circuit that contains both series and parallel components. All right, and then you need to be able to calculate the total current, the current at any given point, and the voltage at any given point of your circuit. All right, so that's where we're at. Okay, so first let's calculate the equivalent resistance of this circuit. So essentially what we're asking ourselves is, what would be, if we were going to make a simple circuit of this, what would be the equivalent resistance? What would we need for one resistor to do the work of all these resistors? So in order to do this, what we're going to do is we're just going to start simplifying the circuit. So what we're going to do is we're going to start with the most complex part, or the part that's like most embedded. All right, we're just going to start simplifying this. So this, what we're going to do is we're going to take this guy right here, and we're going to simplify this. All right, so we're going to redraw our circuit. All right, and so we get this guy here, goes around up here. Now here, though, we're going to combine these two. We're going to find the equivalence resistance of just that guy right there. All right, and then that comes down like this, and then over, and like that. So this is still 6. This is still 4. I'm not going to worry about sig figs. And 1 and 3, and this is still a 9 volt. All right. Now this guy here, both of these guys were in series, and now they're no longer in series. So, or they're in series. So the equivalent resistance for this guy would just be 8. All right. And that's from the previous video. All right. Now we're going to do the same thing. Now the most complex part would be these two combined. So we're going to take this guy and we're going to combine these two here. And so we're going to redraw our circuit again. Resistor. All right, now instead of these guys being parallel, they're just going to be one resistor that has the equivalent resistance here, and then here, like that. So this guy will still be 6 ohms, this guy will still be 1, this will still be 3, this will still be 9 volts, and this new equivalence here, this REQ value, these were in parallel, so now we have to say, well, this is equal to 1 over 8 plus 1 over 4, and the inverse of that. All right, so the REQ for this little subsection here, that parallel component, is equal to 8 inverse plus 4 inverse, in parentheses, inverse of the whole thing. So 2.67. 2.67. All right, so this guy's 2.67. All right, now we can take this guy and we can redraw it. And now that they're all in series, now we'll just have one big guy with just one honking resistor on it, right? We can combine all those because now they're in series. So this would be equal to all these guys added up. So 6 plus 3 plus 1 plus 0.67, or 2.7. So we get a 12.7. So that's the REQ of our circuit. Okay, 12.7. Not too bad. Not too bad. Okay. Oops. All right, so 12.7. All right, now it says, for the 2 ohm resistor, find the current and the potential difference. All right, so for specifically this guy right here, what we need to find is the current and the potential difference of that specific guy. All right, oops. And so what we're going to do is we have to work backwards. Okay, so what we need to do first is find the total current. All right, so we're going to find the total current of this thing here. So this is the resistance, that's the voltage, right? And this is in ohms. So that means the current of this, okay, and it was 9 volts. That means the current of this specific, the overall current here would be equal to, our I is equal to delta V over R. Delta V was 9, and our R was 12.7. So that means the current of this specific, of just the overall current of this guy would be 9 divided by 12.7. All right, so we get 0.71 amps. Right, so that's the current of the whole thing. Now, because we are in, and I'm going to jump between colors here to kind of help us keep track of what's going on. All right, because our this came from guys that are in series, right? Each of these series, remember from back when we looked at our rules for series right here, oops, our series rules, okay, the current at any given point is always equal to it's the same, right? So that means the current here is 0.71 amps. So we'll mark all these guys in green because all of them have their current is equal to 0.71 amps. So all of these resistors have the same value for their current because they're all in series with one another. All right, now we're trying to get to this guy here. This is what we're after, okay? And so we're going to go to that one here. So that means we're going to zero in on this specific resistor set here. Now, because this came from guys that are in current, right, these guys all have their current is equal to 2.67. But because they're in parallel circuits, or parallel components have the same voltage, okay? And so now what we have to do is find the voltage across each of these guys. All right, so what color should we use for that? We'll say color, not erase. We want ink color, I don't know, let's do blue, okay? So now we're going to find our potential difference. Well, delta V equals I times R. Well, our I value here is our current that we just calculated, and it's in green, so that means it's that 0.71 amps. All right, so that's 0.71 amps. And the resistance is our equivalent resistance that we calculated before, so that's our 2.67. 67. All right. Oh, this is where my face is now in this video, isn't it? I'll move myself down here so it's out of the way. All right. So we'll say 0.71 times 2.67. All right, and we get 1.9 volts. All right. So at each of these guys, because they're in parallel with one another, this has a potential of 1.9, and this has a potential of 1.9. All right, so that's easy enough. So that means when we're looking at our original guy here, all of this, because they're all in series with one another, they all have that same potential difference of 1.9. All right, but what it's asking for, remember what it was asking for was find the current and the potential difference at that guy. All right, so we got to find the current here. All right, so the current for this specific guy, all right, maybe we should change colors again. Pointer options, ink color. Oh, I don't know. Do you think purple would be all right? Okay. And so our current here, our current is going to be equal to delta V over R. Well, we just found our delta V. Our delta V was 1.9, right? And then the R value, well, our R value is that equivalent resistance, so that's that 8. So we'll say 1.9 divided by 8. So we get 0.238 amps. So that means here the current across this resistor is 2.238, and the current across this resistor is 0.238. Okay. Then we just need to find the voltage at that spot as well, and we'll just stay in purple because we're right here. All right. So the potential difference here is going to be equal to I times R. Our I is 0.238. All right, and our R value is 2. All right. And really, this will become 0.24 because of sig fig, so maybe we should have. And then there's a 0.24 amps. So maybe we'll change this to 0.24 amps. So the potential difference is equal to 0.48 volts. So this is our final answer. Okay, that guy and this guy here in amps. All right. So those are our potentials. So back the truck up here. What exactly did we do? Well, first thing we had to do is calculate the equivalent resistance, right? So we had to calculate the equivalence resistance. So we broke this guy down and we simplified this circuit, right? So we did it 3 times. We just simplified it. We took this guy in series, turned it into just parallel, turned that into just series, and then we were able to find the equivalent resistance. Then they asked us to find the current and the potential difference across one specific resistor in our circuit. All right, and so that was our 2 ohm resistor. And so what we did here is we took this guy, and because we know this was in series, we could find the current across the whole thing. So that's our 0.71 amps. And then from there, we knew that anything that was in series here was always 0.71 amps. So that's this guy in green. And so that means this was also 0.71 amps. Now, because these guys are in parallel, that means their voltage has to be the same. So we're going to find the voltage across that parallel component, and that's equal to 1.9 volts. All right, and then once we have that, we can go over here, and we know that this top one was broken down into these 2 guys. All right, and then so that we can use that voltage that's shared between the 2 of them in order to find the current that's across the 2 of them. All right, and then we found the current that's across 2 of them, used that to calculate the voltage just across that resistor. All right. We did it. We got all the same answers. All right, let's try this one just for funsies. All right, it says find the equivalent resistance. So we're going to take this guy and we're going to redraw him, all right, to simplify him. So we get this guy, all right, and then, so that parallel guy is going to break down into this. All right, so this is still going to be 3 ohms. And this guy, well, the equivalent resistance, so we'd have to take our Req for this particular point right here would be equal to 1 over 6 plus 1 over 9th, and the inverse of all that. So the Req would be equal to 6 inverse plus 9 inverse, and then inverse of the whole thing, so that would be 3.6. All right. So that's 3.6. So the equivalent resistance of the whole shebang is equal to 3.6 plus 3, so it's going to be 6.6 ohms. All right. Then it asks us to find the current through the 3 ohm resistor. Well, the current through the 3 ohm resistor, remember anything that's in the same series would have to have the same current. All right. So that means the current is equal to, use Ohm's law, delta V over R, all right? And so our delta V, well, that's just the potential difference of the battery, so that's 12, and then the equivalent resistance would be 6.6, right? And that should be it, 12 divided by 6.6, all right? And that's equal to 1.8 amps, right? So that's that guy there. That's easy enough. And we don't have to break that down any farther because he's just one resistor. If this was broken down into something that was parallel, we'd have to do something more, but we don't. All right. Then it says find the potential difference across the 6 ohm resistor. Well, we know that across these 2 resistors combined, okay, that the current is equal to, our I is equal to 1.8 amps. That's the funkiest 8 I've ever drawn. All right, 1.8 amps. All right, so, but we want to find the potential difference across just the 6 ohm resistor. So now all we have to do is just find the delta V, all right, is equal to I times R, and our I value is 1.8, all right, and our resistor is 6. All right, so that means our delta V would be equal to 1.8 times 6, and we get, oh, but sorry. We don't use that because that is the resistor. I'm sure some of you are screaming at your computer screen. We don't use that because that is the resistor. We want the equivalent resistance, which was the 3.6. All right, so 1.8 times 3.6. See, this stuff's kind of tricky. So that would be 6.5 volts. And that's that. So these can be kind of tricky. The only way I know of personally to get better at these is to practice them. And even if you've practiced them and you've been doing it for years, sometimes it's easy to kind of slip up, just like I did real quick there. So anyway, so do your practice problems and let me know if you have any questions, and I'll see you on the flip side.